Hello, my name is Nikola Marincic. I work at ETH Zurich as a lecturer at the Chair of Digital Architectonics and as the doctoral program coordinator at the Institute of Technology in Architecture. In 2017, I defended my PhD thesis titled Towards Communication in CAAD, Spectral Characterization and Modeling with Conjugate Symbolic Domains. In the same year, I received the ETH Medal of Distinction for an outstanding doctoral thesis, and in 2019, Birkhäuser published my work as Computational Models in Architecture. My main supervisor was Professor Ludger Hoerstadt from ETH. He guided me on the topic of digital architectonics and coding. Professor Elias Zafiris from the University of Athens introduced me to category theory through his natural communication model, which I then applied to architectural modeling. And Professor Vera Bühlmann from the Technical University of Vienna supported me in developing abstract thinking that would make it possible for me to identify and integrate different aspects of my work into a coherent whole. With regard to the computational models, my thesis aims to accomplish three goals. First, to position the established computational models in architecture within the broader context of mathematical and computational modeling. Then, it aims to challenge these computational models in architecture with contemporary modeling approaches which regard computation from the perspective of communication between different domains of a problem. Finally, it aims to show how within the paradigm of communication it is possible to computationally address architectural questions that cannot be adequately addressed within the current computational paradigm. The first part of my work begins in the 19th century as it delves into the body of thinking from which computation emerged. It traces two general attitudes toward mathematics and modeling, which will each eventually lead to different interpretations of computation. The first one, that I identified as the logicist tradition, saw the potential of formal mechanized reasoning to construct the absolute foundation of mathematics, but also its means of explanation and proof. The second one, which I identified as the algebraist tradition, regarded formalization within a larger scope of model theoretic procedures characterized by creatively applying abstraction towards a particular goal. The attitude of the proponents of the algebraic tradition created a fertile ground for the redefinition of both mathematics and science, paving the way for the contemporary physics and information technology. Based on the distinctions that I identified by comparing the two traditions, I recognized the discrepancy between the computational models that we use in architecture, following the logicist tradition, and those commonly used in information technology, following the algebraic tradition. The Internet revolution, which was initiated by the development of search engines and social media, indicates the changing role of how we conceive computation in computers from computing machinery towards the generic infrastructure for communication. And in this respect, the second part of my thesis showcases two contemporary models of communication which are both proponents of the algebraic tradition. The first one is the natural communication model by Elias Zafiris, and the second one is glossematics by Louis Hjelmslev. Both involve modeling based on distinctions made within partition spectra that characterizes the modeling phenomena. Furthermore, one can even recognize this very principle of modeling in models applied in quantum mechanics, for example. The theoretical positions formulated in these two models allowed me to devise and implement the self-organizing model. The self-organizing model is a computational framework relating four distinct elements with particular functions and relations between them. This architectonic motif is appropriated from Zafiris' natural communication model, which he built using category theory. One of its crucial elements, an encoding functor, whose role is to bridge two different levels of hypostasis, is implemented using the self-organizing map algorithm. In the last part of the work, I applied the self-organizing model in the architectural domain. First, I utilize its partition and generalization procedures to identify spectral distinctions from a database of floor plan images. Those help me obtain a finite collection of elementary geometric expressions. Similar to how languages work, I attached a symbol to each geometric instance. And one can think about this collection of characters as an alphabet, allowing us to describe any floor plan drawn by employing the same conventions. The identified distinctions allowed me to go a step further and address the problem of similarity between architectural spaces on the basis of their architectural representation. And this task cannot be achieved within a presumed Euclidean notion of space within which we submerge architectural representations in order to describe them metrically by means of coordinates. However, within the communication paradigm, which goes beyond intuitive spatiality, the similarity of representations can be naturally derived. Each floor plan becomes a text characterized by a chain of probabilities based upon its alphabetic arrangement. To derive a notion of similarity of floor plans, we compare them not as images, but as texts comprising of discrete elements, the characters. A peculiar thing about this thesis is its theory-driven methodology. Its outcomes did not emerge from the usual exploratory tinkering with code and some degree of luck. Before implementing anything, I intended to become able to precisely formulate what I was looking for in terms of modeling on a more abstract level. And this part took years and consisted of studying many abstract texts I didn't really fully comprehend. I delved into early analytic philosophy, computability and probability theory, formal logic, quantum physics, abstract algebra, computer-aided design, computer graphics, linguistics, machine learning, and of course, architecture. The reason for such a broad, comprehensive investigation was not to be able to claim any expertise or mastery over these fields. Quite the contrary, it was about operating more architecturally, while at the same time developing the rigor of thinking and also consistency of relating things which is required of academic work. However, once the theoretical framing had been established, implementation occurred almost naturally. It became apparent how to systematically recognize and utilize novel architectonic possibilities within our usual codes and methods. My research helped me realize that the idea that we live in a transparent now, in which we know our codes, methods, models, and even our logic and mathematics with certainty, is an illusion. There is no miraculous synchronization of thinking within the now. Some fields of knowledge are still based on the pre-19th century worldviews in terms of models and thinking. Some are stuck in the 19th century logicism, while some are more abstract, thus more contemporary, like for example, quantum theory. A good indicator is to study mathematics, or at least the number systems employed in the constitution of their models, because mathematics is always at the forefront of abstract model thinking. For example, PageRank, which is a famous algorithm that made Google search possible in the early 2000s, is actually based on a model defined by the Russian mathematician Andrei Markov 100 years ago. And the real danger of the illusion that we have authority over our fields and the associated thinking, which we often call field expertise, is the confidence it gives us. This can close up possibilities of reinterpretation and change within a field and eventually affirming a canon. The way out of the prevailing techno-empiricism cannot be, as it is done today, by employing more technology, but rather by rethinking it on a more abstract level. For that, we need philosophy and we need mathematics, because the thinking itself is also bounded by the abstractions we can conceive and relate to each other and to the world. Thus, we do not need mathematics only as a powerful problem-solving instrument or ally, but as means of engendering cases out of abstraction, as Bühlmann puts it in her text on continuing the Dedekind legacy today. My perspective on that is that, for example, we, architects in the age of AI, should not expect new architecture to simply come as a result of applying an AI algorithm. That would be a dangerous shortcut of the kind that I mentioned earlier. Such shortcut would, for example, allow global IT giants like Google or Facebook or Amazon to systematically codify and commodify our legacy. I hope that the new architecture will more likely come from architects who can expand their general thinking capacity to incorporate the intriguing novel architectonics of thinking and relating that make those AI models possible in the first place. In this way, an architect in the age of AI is an architect who has the ability to think like a computer scientist or physicist or philosopher in terms of abstractions and the price they bring, but whose primary motivation must be in caring about architecture and the willingness to continue its 3,000-old legacy.